Let's get started. Welcome everyone. It is my real great pleasure to introduce Professor Shanhui Fan from Stanford University. Professor Fan did his PhD in MIT in 1997 in condensed matter physics. And he's currently the Joseph and Horn Professor in the School of Engineering. He has several affiliations in electrical engineering and applied physics as well. And he's a senior fellow of the Precourt Institute for Energy. I'm sure many of us here already know about his work. He's published more than 700 refereed journal articles and hundreds of plenary and invited talks. So we are happy to have him here to add to that list of hundreds of talks. But apart from the academic research, he has also been a co-founder of two companies. One of them is Flex Compute, which many of you here I know are using very heavily Type 3 and other softwares. So this is just to say that Professor Fan's work has had a big impact on different industries in photonics and in energy and information technologies. Among the list of awards that I would mention a few of them include the NSF Career Award, the Packard Fellowship in Science and Engineering, the US National Academy of Sciences Baker Award for Initiatives in Research, the Adolph Lomb Medal from the Optical Society of America, and a Vannevar Bush Faculty Fellowship from the US Department of Defense. I believe that is the fellowship that allowed me to do a postdoc under his guidance, and I really enjoyed that time. But apart from all the laurels, I'd like to just mention one anecdote is, if I was talking to Shanhui, I knew that even if I did not explain what was going on in my mind very clearly, he could somehow read my mind ahead of time and explain things better than I could have explained it in my own words. So with that, I'd just like to introduce Professor Fan. The floor is yours, and let's all look forward to stuff. Thank you.
Well, thank you. It's a great pleasure to be here, and thanks, Vic, for inviting me here. My research area is on nanophotonics to try to exploit opportunities of photonics at nanoscale. This is a very broad area, so it's actually hard to pick a topics. So I thought I would talk about three separate topics related to use of nanophotonics and this range from very practical things on energy application, practical in the sense that it actually get me a check every year, all the way to more fundamental things on synthetic frequency dimension, something that Vic started in my group. So I will talk about some of the more recent results. So let me start with the first part on using photonics for energy. The work that I'll be talking about concerns control thermal radiation. This thermal radiation, of course, is a textbook thing, is very well known. And perhaps the most well-known thermal radiator you can think of is a tungsten light bulb. So if you heat up the filament of tungsten to 2000 Kelvin or 3000 Kelvin, it emits white light. And what you can see is that in the standard description of thermal radiator, is broadband and wide angle. Now, what's interesting about photonic structure is that you can create thermal radiator that have drastically different properties. These are some of the pioneering work in the field. On the left here, you have the work from Willie Padilla's group. He is at Duke. And he made these gold nano antenna. So the cross here is made of gold. And I have the scale bar there. If you make a structure like this and look at its absorptivity or emissivity, they are not broadband anymore, but rather are sharply peaked. So you can control the spectral property of the thermal radiation. On the right is the work by John Jack Griffith's group. What he did is he take silicon carbide and put a grating on top of it. When you do that, the thermal radiation becomes highly angular. So the emerging opportunity from the photonic side is that by designing these photonic structure, you can very significantly influence the thermal radiation property. What I like to show today is one set of applications that my group has been pursuing in the past 10 years or so, that is really to try to use this opportunity to control thermal radiation for what we call harvest the coldness of the universe. So the universe is very cold. It has a temperature of 3 Kelvin. And if you learn thermodynamics, you will realize that something that's cold is very useful. The fundamental law of energy conversion, which is the Carnot efficiency limit, says that if you want to have high efficiency conversion of heat to work, then it will be very useful if the temperature of your heat sink is as low as possible. Now, the vast majority of the energy conversion process that's ongoing use the Earth itself as a heat sink at 300 Kelvin. If instead you can use the 3 Kelvin universe as heat sink, you may have a way to systematically improve the efficiency of many of the energy conversion process that's ongoing in this world. Photonics comes in because we have radiative access to outer space. The black curve here is the transmission spectrum of an atmosphere. And the notable feature here is that the atmosphere is quite transparent in the wavelength range between 8 to 13 micron. And that wavelength range coincides with the peak of a 300 Kelvin black body. So the 300 Kelvin is approximately the temperature of every one of us. And also, to a large extent, if we look at our thermal emission spectrum, we are essentially like a black body. So this is, you can approximately think of as the emissivity spectrum for every one of us sitting here. Now, the implication of this graph then is that if you have sky access, in other words, if right now you go out of this room and go outside, then you would be able to radiate heat out through the atmosphere to the outer space. And since the outer space temperature is very low, this represents an intrinsic cooling mechanism. Now, this is, of course, a textbook example of thermal radiation. But in spite of what I have told you about radiative cooling in this kind of concept, if you want to demonstrate it, so therefore you walk out of the room and go outside, it's unlikely you are going to feel any cooler. And that's because the sun is shining on you and that heats you up. So with this, therefore, it would be interesting to think about structures that can actually do radiative cooling during the daytime. About 12 years ago, this is with my, at the time, 2 former graduate students, Eden Raffaali and Ashwash Raman, we wrote the theory paper. So what we envision is a photonic structure that behaves as a mirror in the solar wavelength range, so that it reflects all the sunlight and therefore doesn't get heated up by the sun, but it is black in the transparency window of the atmosphere in the 8 to 13 micron. We did some calculation to show that if you construct this structure and then you put it under the sunlight and you work out the correct thermal insulation scheme, this structure should reach sub-freezing temperature under the sun. And the cooling power, which is the amount of heat that you need to pump into the structure to bring it back to the temperature of the ambient air temperature, exceed 100 watt per meter square. So these sounded like a very strange theoretical prediction when we published it, but we actually take our theory quite seriously, and we look quite hard into experimental demonstration of this prediction. So here was our first experimental demonstration. What we did is we fabricate a multi-layer structure on top of a silicon wafer. So on top of a silicon layer, we put a layer of silver, and that was the reflector. And on top of the silver layer, we put multi-layers of dielectric. Here, the primary thermal radiator is silicon dioxide. The silicon oxygen atom oscillates like this, and that emits thermal radiation near 10 micron. For this structure, is designed to be a very strong solar reflector. As you can see from this mirror, this, by the way, is Ashwas Raman, who is now the professor at UCLA, and this is Lin Xiaozhu, now a professor at Penn State. And you can see that this is a very good mirror, and the average solar reflectivity is about 96%. On the other hand, it has a very strong emissivity peak in the wavelength range of 8 to 13 micron. And so when we bring this thing to the roof of our electrical engineering building, we tilt the sample so that we face the sun. So at the time of the experiment, there are about 900 watt per meter square of solar irradiance directly impinging on the sample. Yet, in spite of the sunlight, the structure actually has a temperature that's about 5 degrees Celsius below the ambient air temperature. And this is done entirely passively, as you can see probably by this picture. There's no wire attached to it. This is done entirely passively without any energy input. And so this actually started a large effort around the world in further developing these kind of radiative cooling materials. And I would just like to show some of our more recent work. So this is one of the works that we have done with Professor Jia Zhu's group in Nanjing University in China. What we did is we do these polymer films. So in these polymer, if you look at the strand of the polymer, they actually have void that are air void on the wavelength scale of the sunlight. Therefore, the structure would strongly reflect the sunlight, and it would appear white. And this is what the picture looks like. On the other hand, a number of chemical bonds in the system emit thermal radiation in the thermal wavelength range. And his group has worked out a row-to-row electron spinning process that allow you to produce these films continuously over large scale, and these does radiative cooling. There are actually many, many materials that now people have demonstrated that are capable of cool under the sunlight. And this is a work, again, a collaboration with Jia Zhu's group, where we look at sub-ambient cooling with nanoprocessed silk. So if you know how silk look like, they're quite shiny, and therefore they're actually a pretty good solar reflector. On the other hand, it turned out that it's not reflective enough from due to the UV absorption of the molecule in silk. So what we did is we take natural silk, and then we attach the fiber in the silk with zinc oxide nanoparticle. When we do that, we can actually enhance the reflectivity just a little bit. This, in combination with the thermal radiation from the silk, will allow you to do sub-ambient cooling. So this, again, is a rooftop setup at Stanford. So as you can see here, in this experimental data, native silk is above the ambient air temperature, but this nanoprocessed silk actually is below the ambient air temperature, even under direct sunlight. So this is an example that, in fact, by engineering textile, you can actually wear your own air conditioner. The radiative cooling technology can also be combined with many other passive cooling technology. One of the very important passive cooling technology is evaporative cooling. And they are actually quite complementary to the radiative cooling technology. Radiative cooler does not need water. So it's, you don't need anything, but what you do need is clear sky. If you have cloud cover the sky, the radiative cooling actually won't work that well. Evaporative cooling, on the other hand, needs water, but it can work in a wider range of temperature, atmospheric conditions. So in this work, what we do is to combine the two together. So this is a system where we have the top layer that are they are made of fibrous network, so these are hollow network. They behave as a radiator cooler, but also behave as a water harvester at night, because at nighttime you can also do cooling. So at night, this top layer will harvest water. The water will then get stored in a hydrogel structure underneath the cooler. Then during the daytime, both the water evaporation and also the radiate cooling, if the sky is clear, can function. So in doing so, one can combine these two cooling mechanisms and to be able to enhance the cooling power, but also to be able to be operational over a wider range of weather conditions. So one of the practical application of this kind of radiated cooling is to do air conditioning for buildings. For a modern building like this, when we do radiated cooling, as you can tell, we're doing it on the roof. Now, for a modern building like this, it's actually very well insulated. So lowering the temperature of the roof does very little to influence the footprint of the building if the building is well insulated. So what you would need to do is to deliver the coldness that you generate on the roof into the building. And so we did this work where we take radiated cooling panel and we put circulating water loop underneath it so that we can get a temperature of the water to be below the ambient air temperature. We then use this temperature to drive a water-based cooling tower. The few degree difference below the ambient air temperature translate into about 10 to 15% efficiency gain in the efficiency. 15% of US power consumption goes to air conditioning. And so this as a passive way to improve the efficiency of air conditioning, therefore is of commercial interest. So together with two of my postdocs, then Eli Goldstein and Ashwas Raman, we founded this company called SPIE System that try to deploy these radiated cooling panel on the roof in California. So this is actually a picture of one of the setup of SPIE system on a supermarket called Grocery Outlet in not too far from Stanford. And you can see the radiated cooling panel here and the water pipe here underneath it that generates the cold water. And that's a company, as I mentioned, that actually do send me a check every year. So as a proof that I have actually done something useful. Okay. As a somewhat more academic work on this side, one of the recent works that we've done, and this is a collaboration with Wei Li's group, a former postdoc now in Chinese Academy of Sciences, is to do radiated cooling of vertical surfaces. So all the work that I've shown you, we use the rooftop. So we have the cooler directly face the sky. But many of our buildings, if you look around, of course, has large vertical surfaces. So it will be certainly of interest to try to use those surfaces for cooling purposes as well. This turned out to be slightly harder, in part because if you put the radiated cooler on the roof, the backside is a mirror. So the ground radiation, the thermal radiation from the ground will be reflected back to the ground and won't heat up the cooler. If you put the radiated cooler in a vertical configuration, now it's going to see the radiation from the ground. So there's an additional pathway of heat input that you will need to block. So the idea is that you will need to design an angular reflector on the thermal radiation side together with the solar and the thermal spectral control of the radiation. And the structure that we did is to take a slanted grating structure covered with a nanoporous polyethylene film. The nanoporous polyethylene film is made of polyethylene, which is like your kitchen wrap, the plastic kitchen wrap, but introduce nanopore in that to scatter light. So it looks white, and it's a strong solar reflector. It turned out to be transparent in the thermal wavelength range so that the radiation can come out. And underneath the nanoporous polyethylene, we put this sawtooth grating. The slanted surface is covered by silver so that it reflects the light that's coming from the ground, the thermal radiation that's coming from the ground. The flat part is made of silicon nitride so they radiate into the sky. So if you look at the solar side of the reflectivity as a function of both angle and wavelengths, it's broadband all angle as you need by the radiated cooling. On the thermal side, what you see is that you see strong thermal radiation only in the angle pointing to the sky and only in the wavelength range between 8 to 13 microns. So that satisfies the criterion for a vertical surface sub-ambient radiated cooling. So this is the experimental setup. This is in Changchun, China. And so we compare 3 structures, a white pent, a standard radiated cooler. These now you can actually routinely get in a number of different ways. And also our angle selective radiated cooler for vertical surfaces. And we measure the temperature of all of them, but I thought that it may be easier to just show a picture. So this is an infrared image. Red is cooler, red is hot, and blue is cooler. So you can see that the angle selective radiated cooler is, in this image, cooler both than the white pent and also in the standard radiated cooler that was designed on the rooftop operation. In fact, neither the white pent or the standard radiated cooler can reach sub-ambient temperature. But if you do the angle engineering of the thermal emissivity, you still can, even on the vertical surface. I hope to use this example to say that there is still a lot of interesting optical design that you can do to tailor this kind of radiated cooling technology to different application scenarios. In the last part of my talk, I'm going to switch gear a little bit, but still think about radiated cooling, but now talk about cooling at night. So doing radiated cooling at night, in fact, is a lot easier because you don't have to worry about sunlight. So pretty much any thermal radiator will cool. One of the interesting opportunities this gives rise to is the possibility to harvest the coldness of the night sky to actually generate electricity. So if you have a radiated cooler facing the sky, its temperature will be below ambient. Consequently, you can put a thermoelectric generator runs between the ambient temperature and the radiated cooler, and you should be able to produce electricity. So in our initial experiment, our radiated cooler is an aluminum plate covered just by black paint, because this is nighttime. And we were able to generate enough electricity so that we can light a light emitting diode. So in this case, this is the title of our paper. We really were able to generate light from the darkness of the night sky. Very large number of materials can be used for cooling, especially at night. So I think this is a cute experiment where we take a photovoltaic panel. Silicon photovoltaic panel is typically encapsulated, meaning that you will cover it with a thick layer of silicon dioxide. And that silicon dioxide layer at night is a great radiative cooler. So consequently, you can take a photovoltaic panel and then put a thermoelectric generator on the backside. And this would then generate power both during the day and during the night. So here are some of the experimental results where you can see that during the daytime, you would actually have power during the daytime, which is here. You will have power coming from the photovoltaic, and also some power from the thermoelectric generator because it's hotter under the sun. Now at nighttime, the photovoltaic panel turns off, but the thermoelectric generator can still generate power. So you could actually use a solar cell in this configuration to produce power 24 hours of a day. Now the amount of power in this case that you produce at night is quite a bit smaller. This is about 50 milliwatt per meter square. So one can further improve it, and this is one of our recent results where we take a thermal emitter, encapsulate it with a vacuum chamber so that we can cut down parasitic loss, We also work on the selectivity, the thermal emission selectivity of the emitter, as well as the contact impedance, thermal impedance matching of the thermoelectric generator to improve the power that we can produce to about 350 milliwatt per meter square at night. And this is electricity generation. So this is nowhere near what you can get out of a solar cell. However, for ambient energy harvesting, this is a record number. And this has potential importance for low power application, for example, in charging a phone, in lighting, or in sensor, off-grid sensor application at night. Now, we are actually a theory group. It's not entirely obvious from this presentation, but we mostly work on theory. So one of the theory questions you can ask yourself is, what exactly is the theoretical limit of the power generation from here? It turned out you can do interesting thermodynamics about it. So in fact, there's a very large literature on solar energy harvesting. You ask, if I have the sunlight coming from a 6,000 Kelvin black body sending into a ambient, and I put a converter on the ambient 300 Kelvin, what is the power, what is the efficiency I can get out of the sunlight? And depending on how you construct this converter, there's a list of theoretical limit ranging from Shockley quasar, which is the standard single junction solar cell, to multicolor, which is a multi-junction solar cell, to Landsberg limit, which is the fundamental theoretical limit. And now, as it turned out, there's a symmetry relation between harvesting incoming radiation and harvesting outgoing radiation. So in what the experiment I show you, we are trying to harvest the heat flux between 300 Kelvin and 3 Kelvin. We are putting the converter on the hot side with outgoing radiation, and you can compute how much power can you actually generate. It turned out that these two are very closely related together, and you can compute the power density limit of this harvesting of outgoing radiation, and the theoretical limit range from 55 watt per meter square in Shockley quasar all the way to the Landsberg limit of 150 watt per meter square. And this number is about 3 orders of magnitude larger than the experiments that we have done. Now, as I mentioned, we're a theorist, so you shouldn't believe record-setting number out of a theory group in experimental effort. And I think this hopefully, at least in my view, point to tremendous potential in further thinking about materials and devices to improve this kind of energy harvesting. So that concludes the first part of my talk, which is on radiative cooling. We are also interested in thinking about these photonic structure for information processing, and in particular for things like AI and artificial intelligence. As a motivation, energy consumption of artificial intelligence is, of course, very important. The concern of it has reached the highest level of the US government, and with also quite an interesting solution of how you should overcome the energy consumption challenge of AI. Now, if expand coal power is not exactly what you are thinking of, then perhaps it will be useful to think a little bit deeper about the energy consumption in the AI algorithm. This is a standard AI algorithm. So a textbook example is you, for example, take a handwritten digit and produce a prediction about what that digit is. And the algorithm is a cascade of a linear and nonlinear linear operation, a linear transformation, followed by an element-wise nonlinear activation. And there are 2 modes of operation. One of them is called the inference. You take the image and you give a prediction. And the other one is called training, because in order for this to work, you have to train the network. In other words, you have to pick the right weight in the matrix. And this is done by sending in a large number of examples in, run the inference, compare with the desired outcome, then gradually tune the weight of these matrices until eventually it works. So the training takes a lot of inference steps. Now, in the case of energy consumption, the important observation here is that the computational cost actually is dominated by the matrix vector multiplication. So, and this provides interesting opportunities for optics, because in optics, you take any linear optical device, you put the input in, and you look at the output. The input and the output is related by a linear transformation. So for example, if you have a waveguide array, the input would have been the amplitude in each of the waveguide, and the output is just a linear transformation of it, and the weight is controlled by how you configure this waveguide array. So consequently, in the past several years, there have been a lot of interest in trying to build up these optical neural network, because in this case, the energy consumption for computing the matrix vector multiplication is essentially zero. The only energy that's required is the energy in the original signal. Then all you need to do is pass the thing through a passive device. Now, so this is a pioneering work from Marin Soliarczyk and Dirk England's group at MIT. So they take this waveguide mesh, as I mentioned, now, and use this to do matrix vector multiplication. So in this case, you have the tunable phase shifter that you would need to train, meaning that these are, for example, thermal optic phase shifters, so you need to control the temperature, and you need to choose the right temperature at each of the phase shifter until the thing can produce the correct inference outcome. So they have done work to show that you really can do neural network computation this way. One of the challenge in this field, however, is that before you do inference, you need to train the network. You need to make sure that it works. And so the way they did the experiment is they first build a computer model of the structure on a computer. They train the computer model to get all the parameters out. And they implement these parameters on the actual physical device. The difficulty of this is that, in fact, it has been very difficult to build high fidelity model of physical devices, especially when the dimension of the matrix become large. And I think this is probably not foreign to most experimentalists in this room, that if you are asked to build a high fidelity that captures essentially everything model of your experiment, if that's what your professor asks you to do, you'll be thinking about it. Okay. So motivated by this, what I like to show here is an alternative way to do it. And this is what we call in situ backpropagation. And in essence, what we're trying to do is to train the physical device physically without building a computer model. The standard way to train physical device, to train neural network on a computer, is something called the backpropagation algorithm. And so what we'll propose to do is to implement backpropagation in situ on an optical chip, where we will backpropagate the error signal physically through chip, and then measure out the gradient of the cost function by physical measurement. A little bit of the math. The idea of backpropagation is, in fact, very closely related to a very interesting piece of math called adjunct variable method. So in many situations, you'll be interested in computing the gradient of a cost function to large number of control variables. So as a simple example, imagine you were given a design problem where you are trying to maximize the power at the detector, and you are allowed to change the permittivity of every single pixel inside this square. Okay, so to do optimization then, you can do a gradient optimization. What you would do is you get the gradient of the detector to the permittivity of every single pixel here, and then you optimize the structure along the gradient direction. Now imagine you have 1,000 pixels in here, then you need to take the gradient in a 1,000-dimensional space. So naively, well, how do you do gradient? You do finite difference. You take each pixel vary the permittivity a little bit. You take another pixel and vary it. So if you have 1,000 pixels, you would need to do 2,000 either calculation or measurement to do the gradient. Now, it turned out there's a very interesting piece of math. The math says that, in fact, to get the gradient of the cost function to arbitrarily large number of parameters, you only need to do 2 calculations. And one calculation is the usual forward calculation. You put the source at where you desire. You look at the field distribution. Then you do what's called the adjoint calculation, where you put the source at where the detector is. Again, you generate a field distribution. Once you have these 2 field distributions, then the gradient of the cost function, in this case, the intensity, with respect to every single pixel permittivity value, can be computed by a simple overlap integral. So instead of doing, as I mentioned, in a 1,000-dimensional space, 2,000 calculations, now you only need to do 2 calculations. So in this case, this method, by the way, underlies, for example, what's called the inverse design that has been very, very important in photonic design these days, but it's also essentially the math of backpropagation algorithm. And so if you look at the gradient information in this adjoint variable method, you see a math that looks like this, and that's the overlap integral between 2 fields. And this, you can read it off by an interference measurement. So imagine that you beat the original field with the time reversal of the adjoint field. The beating term is your gradient. So based on this math, we propose the following 3-step protocol. We do a forward pass. So like the usual inference run, we send a signal forward. We record the transmitted signal. And therefore, we can generate the error signal. In the second step, we then take the error signal, backpropagate through the device, again measure the transmitted field. We then time reverse the transmitted field. Then in the third step, we take both the original field and the time reversal of the transmitted field, send it together into this device. And then if you measure the intensity distribution inside the structure at every single phase shifter in the device, you get the gradient information out. So this is a theoretical protocol that we proposed about 5 years ago. More recently, with collaboration with my colleague Olaf Solgaard and David Miller, we provide an experimental demonstration using a silicon photonic chip that's measured on the foundry. This is a microscope image of the chip. The optical part is here. And then there's a lot of electronic part that controls the phase shifter. I won't go through a lot of details, but I just want to highlight some aspect of the experiment. In order to do this in situ backpropagation, you would need to do a number of things. You would need to be able to generate arbitrary input. You would need to be able to characterize it so you know the modal content. You need to generate the time reversal of any input. And you will also need to read off the field pattern or the intensity near each of the elements that you would need to compute gradient on. So it turned out that in this waveguide mesh, you can generate, characterize, and time reverse arbitrary input field. And in order to get the gradient information, we need to measure the intensity distribution inside the chip. And what we do is near each of the phase shifter, we put a little tap grating coupler to scatter just a little bit of light out in the vertical direction. In this case, if you take a microscope, so you can take an image of a light inside the chip, as indicated, for example, by this image here, the intensity in each of the spot actually contains gradient information that you can use to train this neural network to do neural network computation. So I hope to give you this example. This is one example in thinking about using nanophotonic structure for information processing purposes. to perhaps give you a sense that there really are a lot of potential in these kind of circuit these days in thinking about innovative way to process information. So that concludes the second part of my talk that concerns the use of these photonic structure for information processing. In the final maybe 10, 15 minutes or so, I'd like to talk about some of the more fundamental things, and this is related to a work on synthetic frequency dimension. So the motivation here is to try to program arbitrary Hamiltonian. So we know that quantum dynamics are controlled by Hamiltonian that look like this. Certainly we have been very interested in topological physics. And if you open any of the topological physics paper, it typically start by, I postulate a Hamiltonian of a particular form, and then that go on to tell you all the fancy things that Hamiltonian can do. So for that purpose, if you want to translate that into experimental exploration, then you would like a way to program this Hamiltonian. Now this is a non-interacting Hamiltonian, but controlling this also is very important in enabling a wide range of quantum interactions. So in photonics, in fact, many of the photonic design can be thought of as trying to program this Hamiltonian as well. So on the left here is again, a major work in photonics or electromagnetic. This is a metamaterial for negative refraction. Now, what they do is they create a three-dimensional resonator network. So each of these square-looking thing is actually a resonator. And these resonators, each of them has their unique properties, and also they couple together to form interesting properties of negative index. So in this case, in photonics, if you look at most of the design that we do, it is in fact, we are designing complicated structure in order to achieve specific Hamiltonian as well. Now, this is a fairly sophisticated process. These are not trivial structure to think about. They are also quite complicated, especially when you are trying to do higher dimensional system. So what we would like to do is to simplify the process of trying to create some of these Hamiltonian. And the idea is to trade the complexity. In other words, you need the complexity of this Hamiltonian, but to implement it, instead of doing it in real space, and therefore for each Hamiltonian, you need to think about a particular structure to implement it, we go to frequency space. And in particular, we think of a structure where we have a ring and we put a modulator in there. And then we use the modulator to couple the modes in the ring with different frequencies. This idea has been around in photonics for many decades. In fact, this is the underlying idea for Moloch lasers, which are very, very important in optical science and engineering. And we use essentially the same formalism, but we do it for different purposes. So as an illustration of the basic idea, if you take a single ring resonator, now if there's no group velocity dispersion, then it forms a frequency, a set of frequency cone, in other words, eigenstates, where the frequencies are equally separated, and the frequency spacing, which is called free spectral range, is reciprocal to the round trip time. In this case, if you don't put anything in the ring, these are eigenmodes of the system, so they don't couple to each other. You can couple these modes together by putting in a modulator. So if you put a modulator, and this is a device where the transmission varies as a function of time, and moreover, you choose the modulation frequency to be equal to the mode spacing, then now modes at different frequency will couple, and as a result, you create a one-dimensional tie-binding model. So the modulation strength goes to the hopping strength between nearest neighbor mode, and the modulation phase goes through the hopping phase of nearest neighbor mode. So in this case, you get a one-dimensional physics in this simple structure, but also you get a effective magnetic gauge potential for photons, and that's the hopping phase. So from this, you can do a lot of topological physics. This is our initial theoretical work done by Lucile, who now is a professor in Shanghai Jiaotong University. So it's an attempt to implement integer quantum Hall effect. Now you take an array of rings, and then each of the ring you put a modulator in there, and you change the modulation phase on each of the rings. And this implement a Landau gauge in a two-dimensional lattice. So the two dimension, one of them is the frequency dimension, as I mentioned. In each of the ring, different modes at different frequencies coupled due to modulator. The other one is that at the same frequency, the photon can tunnel from one ring to the other. And so that gives you a two-dimensional lattice. And then if you spatially change the modulation phase, then you implement this Landau gauge of a uniform magnetic field, so that gives you a magnetic field. So consequently, this system actually supports a one-way edge mode. So if you excite the first ring at a frequency here, then it will go around the edge until it reaches a frequency boundary, at which point it's going to propagate across the array spatially to the other side, and then the frequency is going to downshift. In a picture, this looks very much like a standard one-way edge mode, but the interesting part is that part of the dynamics occur in the frequency space. So that's the maybe a bit of theoretical background. Now let me mention some of the experimental background. So as I mentioned, if you take a ring, modulate it, you get a one-dimensional tie binding model. This model is periodic, so you can define a band structure. You can talk about eigenenergy as a function of wave vector. The somewhat amusing part here is the wave vector. So this is a wave vector that describes the dynamics of photon along the frequency axis. And that dynamics is time. So the variable that's conjugate to frequency is time. So therefore, the wave vector here is in fact a time variable. In other words, if you measure the time-dependent transmission, you can read off the band structure of the system. So in particular, you can take a laser, and then there's a modulator here that the transmission varies as a function of time. So for each of the frequency, you can take out the transmission as a function of time, then you vary the laser frequency, you will get a two-dimensional diagram that looks like this, and that should give you a measure of the band structure of the system. So Avik came to my group to initiate this experiment. So what he did is he make a fiber loop. So this is a fiber of 10 meters, and with a free spectral range about 15 megahertz. And inside we put an electro-optic modulator. These are lithium ion modulator with a modulation frequency up to 2 gigahertz, so that we can do long-range coupling. And we have a narrow linewidth laser where we can do frequency sweep. And on this side, on the detector side, we have a fast detector system so that we can do time-dependent measurement. And here are some of his data. So let me see if I can get this to work. So on the right, each of the curve is a transmission as a function of time for a particular laser frequency. So as you tune the laser frequency, you can see sometimes there are peaks, and then these peaks will move when you change the laser frequency. If you take all the data on the right and plot that on the left in the two-dimensional graph, now you can see the band structure, which look like a cosine of a tie binding model. So one can indeed read off the band structure in these systems. So up to this point, I show you an example of using a single ring to create a one-dimensional system. Turned out that you can create a two-dimensional system or even arbitrary dimensional system as well by long-range coupling. So here's an example where you take the modulator and then you put in two modulation tones, one of them at the free spectral range, the other one at the integer multiple of the free spectral range. You can plot this in a 1D model, and then you just get a long-range coupling. Or you can plot this in a 2D model. In this case, you will get a 2D model where it will have infinite infinite size along one of the dimension, and then has finite size in the second dimension with a twisted boundary condition. So this is in fact very much look like a carbon nanotube kind of Hamiltonian. So now with this, if you choose the modulation frequency to be large enough, you can probe two-dimensional physics. So in the past several years, we have done quite a few experiments using this platform. One thing I should mention is that you can see that in going from one dimension to two dimension, we actually didn't have to change the physical structure. All we need to do is to change the modulation waveform that we put on the modulator. And that's something that you control electronically with a computer. So maybe a naive statement would have been all you did in going from 1D to 2D is that you change one line of a Python code. And that's, of course, very different compared with a real space experiment. So I would just want to show one recent experiment that we have done, which is to try to explore non-abelian gauge field. If you have a particle with spin, it coupled to non-abelian gauge field, and that can be thought of as a direction-dependent spin rotation. This is obviously important for this audience, because that's the fundamental description of particle physics. And there aren't that many good experimental platforms to explore the consequence of non-abelian gauge field, at least from an engineer's perspective. It's not that easy to engineer the interaction of quark, for example. So what we like to do is to explore some of the consequence of these fields, but in a more experimentally accessible way. And so we look at this model, and this is the SU2 lattice gauge field model. And each of the lattice side has a SU2 spin, and the spin can hop. The spin can rotate as a hop between nearest neighbor side. So AX is the gauge potential that controls the hopping along the X direction. AY controls the hopping along the Y direction. Now, the non-abelian physics in this case will occur if AX and AY doesn't commute. So one of the interesting point about these non-abelian lattice gauge field model is that you get non-trivial physics even though the system is completely periodic. And this is not something that you can get in a U1 gauge field. You always have to chirp the gauge potential. So one of the consequences is you can look at the band structure. If you have a non-abelian gauge field, for example, the AX and AY doesn't commute, you work out the Young-Mills Hamiltonian and you work out the band structure, you will see that it actually has Dirac point at the gamma point. This is actually somewhat unusual. Dirac point is very well known in condensed matter physics and photonics. For example, if you look at graphene, it has a Dirac point, a K point. But the K point is not time reversal invariant. Having a Dirac point at gamma, which is time reversal invariant, actually is a little bit unusual because it requires time reversal symmetry breaking. And that's precisely what those gauge potential, the non-abelian gauge potential that I showed, give you. And also, this Dirac cone at gamma is a unique signature of the non-abelianness of the system. For the same model, if you do a abelian matrix potential, you don't get Dirac cone, you get a nodal line. So with this as a background, we try to implement it in the synthetic frequency space so that we can actually explore some of these theoretical consequences of non-abelian gauge field. In this case, for the SU2 model, we use the spin. For the pseudo spin, we use a two polarization in a fiber. And we separate the polarization out so that we can create different modulation on each of the spin, and that to implement the non-abelian gauge potential. Also, we have a time concatenation scheme where in the voltage as a function of time, we have frequency component at both the free spectral range and the integer multiple of free spectral range so that we can do two-dimensional model. With this, we use the same band structure measurement techniques that Avik started in my group to measure a polarization-dependent band structure. So here are some of the experimental results. In the way we measure, we sample along lines inside the first Boolean zone. If these lines pass through the gamma point, the theory indicates a Dirac cone. And that's exactly what we see experimentally in experimental measure band structure. If, on the other hand, you move it away from the gamma point, the theory predicts that you should see gap. And that's something that you can see experimentally as well. So here's one example where we do a non-abelian vector gauge potential that gives you Dirac cone. These Dirac cone can actually be gapped by, in addition, introducing a non-abelian scalar potential, and that's what we actually experimentally demonstrate as well. So with that, I think I'm out of time, so let me briefly summarize. As I mentioned, I chose a somewhat diverse set of topics with the hope that to tell you something about the breadth that you can do in the field of nanophotonics. You can certainly do useful things, but there are also interesting fundamental things that one can continue to play. So with that, let me stop and thank you for your attention.
Very nice presentation. So I have a couple of questions related. The first one is very about cooling and using that as an energy source. So have you thought about the thermal, the geothermal?
Yes.
Yeah, because the temperature underground is very high, and somehow use them.
So that's a very good question. There's obvious geothermal implication for this kind of technique. Now, for geothermal, one of the challenge is you need to implement a sufficient scale. Many of the standard geothermal scheme that people proposed do not by itself have value other than geothermal. For example, if you spray particles in the atmosphere, right, to reflect sunlight, there's no motivation for doing it other than geothermal. What we do here, people would do it independent of the geothermal implication. And we think that may be actually a practical way to think about how one should do geothermal. You want to have something where people are going to spend money to do it anyway, even before you implement a large scale.
I have follow-up theory questions. It's very interesting you can simulate gauge theories with the structures.
Right.
So one of the original formulation of Kim Wilson calculating
right.
non-including gauge theory
is
to implement in a way it's gauge invariant. So therefore you have the gauge fields which implement as like uniform matrices.
Right.
So in those structure here, is that obvious that you can somehow formulate it in a way that is completely gauge invariant?
First of all, I want to make sure that in this gauge field demonstration is not a dynamic gauge field. So it's an impulse gauge field. The Hamiltonian is gauge invariant in that way. But it would be very interesting to do dynamic gauge field. And that's something we're quite interested as well.
Those structures you have, they're by nature, it's quantum, right?
So, right. So the way we do it, of course, it's a non-interacting Hamiltonian with an impulse external non-abelian gauge field. Yeah. So you can call it quantum, but I think many people will object to it. But it is quantum, I would have said. Yeah.
I guess taking one question and just follow that. Since it's an external imposed gauge field,
yeah.
One can still say that X and Y are non-commuting dynamic variables?
They are non-commuting matrices. Yeah, they are not dynamic variable because there's no dynamics associated with it. Yeah.
Thank you for the really inspiring talk. So I had a question about the last part of the optical neural networks slides, where you showed us the mesh for the in situ training.
Yeah. Yeah.
Is there is it just an architectural choice for the triangular mesh that you've implemented, or is that a requirement for being able to implement your in situ?
It's not a requirement, but one thing that's interesting about the triangular matrix is there's a progressive way to implement arbitrary unitary matrix. So, and that's very useful. And also, by reading off in this triangular mesh, by reading off the temperature at each of the phase shifter, you get a complete characterization of the modal content. And so those are very attractive for our purpose. It's not required. You can use other mesh architecture as well.
Thank you.
Following up to the question about like quantum classical versus interacting, non-interacting, would it be possible to introduce interaction in the last part of the like the non-abelian gauge field? Is that
Yes. So for example, fiber has nonlinearity. So there will be interaction that way, and one can also couple these fiber with other systems that have stronger nonlinearity. One of the ongoing work we have been doing is to introduce a squeezing type of Hamiltonian into this kind of system that gives you a pair generation Hamiltonian together with a hopping Hamiltonian, and there are interesting physics associated with those Hamiltonians as well. So I think there are a lot of things that one can do in the future.
So a follow-up question actually regarding the interactions. On platforms like photonics, is it possible to get very strong interactions such that you see phase transitions in these topological lattice models?
That has always been a challenge, I think. There are many people who have done very interesting work. I think Professor Hafezi here, for example, thinking about people have really trying to couple the photonic system to systems with very strong nonlinearity. So I think it will be very interesting to look along that direction.
I had a question regarding the long-range interactions which you showed in the lattice and the transformation to a two-dimensional lattice.
Right.
Essentially, I would like to know whether certain connections between the lattice points could be removed or deleted depending on how we perform the long-range since it's time.
Right. So in this particular setup, because of for simplicity, we chose a setup where a single modulation, for example, omega r here, this is the short range one, couple every pair of the system. In that case, you couldn't just selectively remove one bound. But if the underlying frequency lattice is n-harmonic, and for each of them you put in the modulation frequency, then you can create any defects you want to. But at the cost of a much more complex modulation pattern.
So, is it a possibility to like generate like cluster states on these lattices and see the evolution of that cluster state by controlling these modulations over time?
I think if you do the squeezing type of Hamiltonian, there are more possibilities for synthesizing quantum state. At present, this is a non-interacting Hamiltonian. But I think there are pathways towards it in a more complex Hamiltonian.
Yeah, so to what extent can we actually control these coupling terms? So for example, if I want a model that only has nearest neighbor coupling and next nearest neighbor coupling.
Right.
Can we actually program that modulator to get specifically that?
Yes. So in fact, that's what we show. In other words, if you chose the specific way, the voltage as a function of time that you put on the modulator, you can control the Hamiltonian terms.
So like, can you even build a Hamiltonian that has arbitrary coupling and then tune those couplings?
In principle, yes.
Just more crazy signal.
It's a more crazy signal, right? So just give you a couple examples. I have In this particular case, I've chosen the modulation frequency to be equal to the free spectral range, where you get a periodic model. If you slightly detune it, you get a effective electric field onto the model. So it's not periodic anymore. And you can see block oscillation and many things. So there are many, many things that one can actually think of, because this time dependency of the voltage is, you can think of many crazy stuff.
Yeah, so and the second question is like, if for the original Hamiltonian, in some slide I don't know, but like, if you want to add, for example, current nonlinearity in synthetic frequency space,
Right.
next to your linear coupling terms, like,
Right.
what should you do? Like, can you just make the ring resonator with current nonlinear waveband, or you do something more?
So the fiber has current nonlinearity.
Yes.
If you look at how that map into the synthetic frequency space, it gives you essentially a long-range all-to-all coupling on the nonlinear side. And that can be of interest, but that's not the local Haber model that you may be interested in. We have written a paper a while ago showing that if you control the dispersion of the fiber together, you can actually synthesize a Haber-like model, a Haber model in the system. Or alternatively, you can imagine coupling these fiber system with atomic degree of freedom at fixed frequencies to implement a Haber-like model.
What kind of atom? Two-level atom?
Two-level atom, for example.
Just the two-level atom?
A few of them, so that they have a different frequencies, for example. Because imagine that you have a setup where you have a set of two-level atoms, each of them had a frequency, and that are matched to one of these lattice sites. Then you do get a Haber-like model.
Oh, yes.
Yeah.
Yeah, so maybe I'll ask a simple question. So in the next slide where you showed the cuts to the Goodman zone, how do you choose the starting point where you're starting to scan across the Goodman zone?
That comes from the relative phase of the two modulation.
So here you are more controlling the relative phase of the modulation than the time that you're scanning.
Right, yeah. It controls the relative phase that allow you to scan through different slides inside. The time is a variable along these lines.
We had quite a few questions. If there are no more questions, let's thank Shanhui once again.